So Task 7 is out. I don't know how many of you are ready to start thinking about Task 7, but just to give a brief preview of it. Task 7 is the last testing task, and lessons learned from Task 4. It is definitely restructured from what Task 4 was. So Task 7 was intended to be like Task 4 in that you write all the tests for Task 8 and 9. So that is not the case anymore. We're abandoning that strategy pretty quickly. So you will be writing the code for the test and the code for Task 7. But this also means that you're not writing the tests for Task 8 and 9. So Task 8 and 9 will contain their own tests. So Task 7, 8, and 9, you're writing the test and the code for everything that you do in those tasks. So the workload, like instead of Task 4 being a lot of the work of 3 different tasks, we're just spreading that out and just having 3 tasks that are all fairly similar in the amount of work that they require. Whereas Task 4 was way up here, then Task 5 dropped way down, and Task 6 was a little higher than Task 5, at least in my opinion. Task 7, 8, and 9 will be fairly straight in terms of difficulty. Maybe not. Task 9 is going to be a little tough. But anyway, so Task 7 is all about reading files. We're both going to write code that reads files and then write tests. Hopefully you're writing the tests first. I said those backwards. Writing tests that test code that reads files. So you're going to write code that reads files and also write tests where you're generating test files with data and then running the code on that file and then checking that the expected data is returned from those methods. We're going to parse 2 types of data. Movies data, which I should just open this. It didn't open it in the other lecture. It's just downloads. No, I already downloaded it. Movies data, which is going to contain the title. Oh, it's going to open in a spreadsheet. It's a CSV file, but it by default opens in a spreadsheet. The name of each movie, and then the cast as a CSV file. So we can get that title and cast, like our movies type, our movies class is expecting in its constructor. So we can parse this data and create a bunch of movie objects. And there are a couple movies in here. 5,805 movies. So with data, we want to be able to work with large amounts of data, with files. With files, we want to be able to work with large amounts of data. We're never going to code all of this information in our code itself. We're going to store a file and then have our code read this file, go through every single line, and populate a data structure with all of this information, or process it however we want to process it. So that's our goal in Task 7. We're also going to use... delete it. We're also going to use song rating data. This is where we wrote all that ratings code. We're going to start rating our own songs. So you can go to this site, and please add songs, rate songs. Let's get some data in here to work with. Enter your UBIT, and then you can add songs and rate the songs that have already been added. So we can get some data to work with, some live actual data. And then there's this ratings.csv, which is going to give you all of the ratings with the ID, the song ID, the artist, the title, the reviewer ID, which is numbers in the... they happen to be numbers in the app, but because I don't want to leak UBITs, but it will be represented as a string in your code. So make sure that stays as a string and not converted to an int. And then finally, the rating of that song, this reviewer gave this song this rating. So that's the CSV that we want to parse for song data. So let's learn how to parse files. So we want to, wrong button. Where am I? My mind's still on break. remember my keyboard shortcuts. All right, so we need to learn how to read files if we're going to read this data. So let's do exactly that. So any questions before we get into it, before I just get into the content? Trevor's not going to tell me why keyword args are a design flaw. I want to know what he means by that. I kind of like keyword args. Yes?
Different types of files get opened in different ways? Or like
Kind of.
data be stored differently than other?
Would different types of files be stored in different ways is the question. You do have to, so the underlying way a file is opened or read is always as bytes. Every single file is just bytes. That's all it is. The way we're going to read files, we're going to read the lines of a file, which means we're going to interpret those bytes as text. So the method that we're doing is strictly for text files, but if we could use a different method, we could read all the bytes of a file to read any arbitrary file. And then depending on what file type it is, those bytes are going to mean different things. So if I open a JPEG versus an MP4, the bytes are going to mean different things, but it's all just going to be bytes. And then I'd have to look up my corresponding file type. Okay, how does JPEG store its files? And it's going to have values in different locations, and I can make sense of those bytes. For text files, it's all, for our purposes, ASCII text. So read all lines, the method we're going to use is going to use the ASCII chart and convert all those to characters so we can read the file contents. So the shorter answer to the operating system, it's all just bytes. And then it's our job as software engineers to make sense of those bytes. So why files at all? Why are we even bothering with files? We have data structures after all. Why do we need files to store our data when we're storing data in data structures? So there's a big difference between these two things. Let's talk about it. And by the way, I'm sure you've all seen file I.O. in 1.15, so this should be somewhat review. But I just want a refresher on why we even bother with files at all. The data structures are great at storing data within our program. But the data stored in a data structure, one, it doesn't exist before our program starts. We have to create all our data structures, and we have to populate all our data structures. And two, once our program ends, the data structures are blown up. They all exist in memory. Those data structures are stored on the heap for our specific program. And once our program ends, that data is gone. It's gone forever. And since we have to populate the data structures, when we're doing something like writing tests, when we want to write a test that tests a method that either takes a data structure as a parameter or returns a data structure, we have to manually create those data structures. We're writing new song, song.add rating, song.add rating, song.add rating, and then creating this data structure and then sending that to our code. We have to really manually do a lot of things with that data. The difference between files is its persistent storage. Files live before our program starts, and they'll live on after our program ends. They're bigger than our program, they live outside of our program, and they're outside of the control of our program, which is going to be an interesting topic when we get into this. We don't control these files. They exist as a separate thing on our hard disk, our hard drive or disk. We say they're saved on disk. That's separate from memory, which is our RAM sticks. Files are stored in the hard drive, which is disk space. And persistence is the big reason. Hopefully they hammered that in your heads in 1.15. Files basically equals persistence. And you even talked about databases to be able to manage your files in a more efficient and more structured way. So let's read a file. This is how we're going to read a file in Java. I promise this is as easy as I can make. Actually, not quite as easy. This is about as easy as we could possibly make it. And it's still more complex than Python was for opening files. When you just did with open file as file, for line in file. It's pretty simple in Python. Java's got a little bit more overhead for us because that's what Java does. So let's talk about it. Pass.get of file name. You can't just open a file by its file name. we're going to create a path for that file name. So we're importing the path class, which has a static method named get, which is going to take a string and then create a path out of that string. Because files, you just can't open a file name. You have to create a path of it first. I forgot what I said. Is that called method overloading, or are you talking about what Trevor said? So method I'll just define method overloading, and hopefully it'll answer your question. Method overloading is when you have two methods with the same name in the same class with the same return type, but different parameter lists. So you have multiple methods with different parameter lists, and you can call it with either parameter list. And we've seen that before throughout the semester. We've seen on screen right now. Array list, you can call array list with an empty constructor, which just creates an empty array list, or you can pass a data structure in the constructor, specifically a list in its constructor. So it has it's more than two, but two constructors that we're talking about. Same name of the method, name being array list because it's a constructor, same return type, it returns a reference to an array list, but different parameter lists, either empty list or taking a list as a parameter, and then creating an array list with the contents of the list as its initial values. Which does, I think you were responding to Trevor, which does kind of replace the need for keyword arguments, but I don't know, I like keyword arguments a lot better. Where I believe Python doesn't have method overloading. Scala didn't, I know that one. So we create the path, and then we're going to call the static readAllLines method from the files class, and that's going to, as the name implies, read all the lines of the file. And let's get this disclaimer out of the way because I'm sure some of you are upset. Those of you who have read files in Java before should be upset about the code that's on the screen. So let me just take a quick side note to talk about that. This is a very inefficient way to open files in Java. This is unbuffered, meaning the entire contents of the file are loaded into memory. The entire contents of this file will be in an array list on the heap, all at one time, which can be very bad if the file is huge. If we have a very large file, especially if the file gets to the size of gigabytes, this is going to be very bad. It's going to use up a lot of RAM. Your RAM usage is going to spike like you have a Chrome tab open, and you're going to lose a lot of performance if you're doing it this way, if you're opening the entire file. A better way, especially when you're handling large files, to read files in Java is to buffer the input. And if you just go to Google and you say, Google, how do I open a file in Java? It's going to show you 100 links to the buffered way. This one is going to be pretty hidden among all those results if you're just saying, how do I open a file? Most of the results are going to have you create a file reader and then put that in the constructor of a buffered reader, and then you're going to use that as use an iterator to be able to check if there's another line to read in the file, and then read the file one line at a time. This is called a buffered input. This means that instead of loading the entire file into memory, you're going to open the file but not read it, and then each time you go to the file, you're going to read a single line, load one single line into memory, process that line with whatever you're going to do with that data, and then go to the file again and read the next line, load that into memory, and only read one line at a time, load one line into memory at a single time. So it's much more efficient in terms of memory usage if you're buffering your input. And in general, especially, again, large files, you should be buffering your inputs. Anything that's over a couple megabytes. We're going to read the movies. Oh, I forgot. 800K, 900K. It's under. My goal was under a megabyte, and I got it under a megabyte. So less than 1 million bytes we're going to load into memory, which sounds like a lot, but to a computer that's nothing. We can store 1 million bytes in memory quite easily. But once you get into the order of gigabytes, that's when you really want to start thinking about this. If you're loading a gigabyte file into memory, you're going to notice that RAM usage. So you want to do something about that. And if you have a file that's 20 gigabytes, You can't do this. You can't just read the whole thing into memory unless you have a lot of RAM. But if you got 16 gigs of RAM, you're not even loading that whole thing into memory. You just can't do it. Plus, Java usually will complain long before that. Java will say, hey, you're using a lot of heap space. Like, maybe tone it down and crash your program. So a lot of things to worry about with that. For this course, all the data that we're going to use is tailored to make sure it's below certain thresholds that you're not going to run into this issue. But outside of this class, and I'll give this warning a couple times in different contexts, outside of this class, do things differently. But we're going to use it this way. We're going to open files this way because this is by far the easiest. Still not quite as easy as Python, but this is by far easier than the other method. If you're interested, just Google how to open a file in Java and look at the other way. It's not too bad. We could get through it, but it's just a distraction from the actual learning objectives of the course. It's just something that isn't that important compared to what we want to teach you in this course. It will be important by the time you graduate. You better be doing it that way and understand how iterators work and buffering and all that stuff. Second semester, not so much. We're going to avoid that conversation, even though I just had the conversation. But we're going to avoid asking you about it on an interview and forcing you to do it that way in the code. So, the read all lines, another conversation we're going to avoid. I think there's 3 things in this lecture where I'm going to use that same theme, just a conversation we'll avoid. Read all lines returns a list, which is an interface, and it'll return a concrete data structure that implements the list interface. We haven't talked about interfaces yet at all. We could just use the list. If you want to just use the list, that's fine, as long as in the homework, if it says return an array list, you convert it to an array list by the end. But to avoid that entirely, if you don't want to think about lists, if you just want to stick with array list, which I'm completely fine if you want to, create a new array list, and then in the constructor of the array list, you can give it a list, and it'll create an array list with all the data in that list. So then we don't even have to think about that read all lines returns a list. We're just going to wrap it up in an array list and then use array list. So array list for everything, cool. We already have array list, hash map, linked lists, trees, and eventually graphs. I think those 5 data structures are fine for 116, and then you have a whole class on data structures next semester. We don't have to add a 6th one just for fun. So you can wrap it up in an array list. So that's how this code is working. And then it'll return an array list of strings where each string is a line in the file that was read. But wait, this is dangerous code. This is very scary code. We're taking a string, which is supposed to be a file name, and then looking for a file with that name and opening and reading the contents of that file. This can go very, very wrong. This is a dangerous thing to do when we're running our code. Things can blow up easily, namely if the file doesn't exist. This file might not exist. This file might not exist, and there's nothing we can do about it. We cannot guarantee that file will be there. Files are outside of the control of our program. We got our stack space. We got our heap space. That's our control. Nobody else can touch that. No other process on the machine can violate our space, or at least shouldn't be able to. In rare circumstances, there can be security things, but nobody should be able to touch our memory. We have full control over that, and that's, we like that control. When we're going to disk and reading a file from disk, we have no control over that. We can't control if that file even exists. Because any process on the machine, any process on the device, and the end user themselves, through whatever GUI process they're using, can modify that file at any time. So even if we wrote code, we can write code that checks if the file exists, and then if it exists, we'll open it. But we can run the check. What happens when we run that check? And then after the check runs and we say the file exists, we're going to go open it. And right in between that, in that split second, that few milliseconds after we run our check and before we open the file, someone deletes that file. Or another process deletes that file. Now when we go to open the file that we just checked, we're sure it exists. Well, it doesn't exist. What if we're halfway through reading the file? Maybe it's a pretty large file. It takes us a while to read it. It's taken half a second to read it, maybe. Maybe it's that large of a file. And while we're reading it, someone deletes it. What if somebody modifies the file as we're reading it? There's a lot of things that can go wrong here because every process on the device can have access to that file and can delete it at any time. So we want to be careful of that. The file might not exist. Nothing we can do about it, no matter our best laid plans. Now, granted, it's pretty rare. If we do have the check to see if the file exists and then open it, it's pretty rare that somebody's going to have that exact timing. But maybe there's a process on the machine that's looking to see if a file was accessed at all. And when the file is accessed, it modifies, like updates the last modified date or something. So the file's slightly different by the time we read it. And then something weird can happen with that corrupts the file. Some things can happen. Like things can happen in that split second. So anyway, that file opening can throw an exception, specifically the read all lines file. The read all lines method can throw an exception. So let's talk about what exceptions even are before we move on. So exceptions are thrown whenever a method is called that runs into something that it doesn't handle. Something that the method doesn't do, it has every right to say, I don't do that, and then throw an exception. If the exception is uncaught, so we have a little bit of vocab to learn here. If the exception is a thrown exception is uncaught, the program crashes. And you're seeing this all the time. We've seen quite a few exceptions that are thrown and uncaught. If you have an index out of bounds exception, you try to access a value in an array of size 4, and you ask it for the value index 10, you're going to get an index out of bounds exception thrown by the get method. And then if you don't catch it, program crashes. You see all the error messages, and things crash. Null pointer is actually an error. I was called out on this in the last lecture. It's an error, not an exception, which means there's nothing we can do about it. If we run out of, stack overflow error. If the stack is overflown, there's nothing we can do about it regardless. That's just going to crash the program anyway. We can't catch it. Null pointer exception we can catch. Null pointer exception, you've seen these things before, and usually they're uncaught, these ones that are on screen anyway. And a lot of times that's the behavior we want so far, a semester and a half into your programming career. That's usually what we want. We just want the exceptions to crash the program because those exceptions are usually bugs in the code that we have to fix, and we're going to fix those bugs before we release code to the public. We want to just let those exceptions, what we say, bubble up all the way up to the main method without being caught, and then crash the program. When the program is crashed like this, it'll print out the stack trace and the exception type. So you've seen this in IntelliJ, but just to explain what it's actually showing you, it'll tell you the exception name and sometimes some extra error message associated with that exception. And then it'll print out the stack trace, which is it goes to every stack frame that was on the stack when the exception was thrown and ask it, hey, what were you doing when this exception was thrown? So you see all the stack frames will tell you which line of code it was executing and which character on that line it was executing when the exception was thrown. So all the methods except the last stack frame, all the stack frames except the last one will tell you what method it called that threw the exception. Then the last one will say exactly where in the code it was when the exception was thrown. And you click on the blue link, that stack frame takes you right to that line of code, that character in that line of code. And you can help use that to help your debug process. So that's an uncaught exception. So if we don't want the program to crash, we're going to catch that exception. We're going to do that like this. In fact, if we just write this line of code, the IO exception and several other exceptions, but IO exception, which is what this is going to throw if the file doesn't exist, Java will not let you write that code without handling the exception one way or another. We're going to use a try-catch block. Without this try-catch block, the code actually wouldn't compile. So the code we've seen so far doesn't even work. We need this try-catch here. So we're going to catch the exception. The way we do that is with a try-catch block. We're going to try to run the risky code. And if an exception is thrown, we can catch any exceptions that we want. So we're going to catch the exception, and if the exception is thrown, we're going to run what's in the catch block. So we try to run this code. We expect this code to potentially throw an IO exception. It might throw other exceptions as well, but IO exception is the one we're going to catch. If it throws an IO exception, or any exception, whatever is running in the try block will stop. Completely stops, just like if the program is about to crash. It'll go through the same process. It'll stop executing any code. So if I have another line of code after this line in the try block still, and this line throws an exception, that next line will never be executed because we're throwing an exception that stops everything, stops the execution, clears off the stack up until we're back in this method, exit the try, and then go into the catch. So if this throws an IO exception, we're going to catch the IO exception and run this line of code, which my box got a little off center. I don't know how that happened. But we're going to catch the IO exception. So if the risky code in the try block throws an IO exception specifically, we're going to catch it and run the code in the catch block. And the syntax is very similar to a parameter list. I'm going to catch an exception of type IO exception. I'm going to name it E. I'm not actually doing anything with that variable. And then I'm just returning an empty array list. So if the file doesn't exist, I'm just going to return an empty array list instead of crashing the program. We don't want to crash the whole program. For what it's worth, we can have multiple catch blocks. I could have another catch block down here that catches a different type of exception. So if you're running code that can throw multiple different types of exceptions and you want to handle each exception differently, you would have multiple catch blocks for each type of exception that can be thrown. And every exception does extend the exception class, so you can catch exception E without specifying the type of exception and just catch everything. Not recommended to do that, but you will see that at some point in your career if you haven't already. You'll see that code. And you should say, you know what, we should probably break that down into separate blocks, handle exceptions differently, depending on what the application is. I mean, for a hackathon project, whatever, but for production code, you wouldn't want to do that. So now the program doesn't crash. We're going to stop execution in the try block, move over to the catch block, and run that code and not crash the program. That's the important part. Without the try catch, this program would just break. Well, it wouldn't even compile in this case. We're going to catch that exception. So this code overall is going to try to read the file. If the file exists and everything goes okay while reading the file, we're going to return an array list with all the lines of the file and then return that. If the file doesn't exist or anything else goes wrong, any IO exception is thrown, we're going to return an empty array list, which is consistent with the homework. For the homework, each of the methods you'll write, if the file doesn't exist, return an empty, I think they're both array lists, return an empty array list. Any questions on reading a file or throwing exceptions or catching exceptions? Bless you. Nothing? So it's not too much. I mean, it's a bit more than reading files in Python, but I don't think it's too much more. And we get to talk about exceptions, which is something you'll want to know about in your career. Interesting or not interesting, depending on how you feel. Scala didn't have exceptions at all, so you do get to hear about exceptions. Previous classes have to learn about them some other way. When we taught this in Scala. All right, string parsing. So we want to read CSV files. We can read the file itself, but now each line, how do we process those lines? So let's talk about a little bit of string parsing, something we haven't talked about yet this semester. Again, a lot of it's similar to how we did things in Python, but slight differences. So let's talk about Java specifically. And let's get a disclaimer out there. Got another disclaimer for you. We're going to read CSV files the wrong way. We're not going to do this the right way. So CSV files, comma-separated values, we're just going to split them on commas. Take a line, split it on comma, and then get the values that are comma separated. This isn't the right way to parse CSV. CSV, the format is a little more complicated than that. So there are a few choices here that Paul and I had to sit down and make of how we want to do this. So what can go wrong is a CSV line, a value in a CSV line can contain a comma. It's valid for data to contain commas. And if you just split on commas, you're going to chop that piece of data in half, which won't parse correctly. So this won't parse general CSV values, CSV content correctly, because if the content contains a comma, then it's going to bust up the data. So for CSE 116, all the data we work with is carefully curated to not contain commas. If you add a song to the song ratings app where a title or artist contains a comma, it's just going to straight up remove that comma on you. That comma is not going to exist. So, and in the movies, any names that had commas, they're all just removed. So we don't run into that issue. The way the format does it is if a value contains a comma, it'll surround that value in quotes. So when you find a quote, you're entering an escaped state, and your commas are part of the value at that point. And then when you see another double quote, commas go back to meaning separating values. So that's the way the format actually handles it. So the choices were either have you write a parser that looks for the quotes and escapes commas based on the quotes and validates the CSV format, which Paul and I decided that's way too much tedium to put you through. It's a pain in the ass and has very little to do with what we're trying to teach you in this course. So don't want to go that route. We didn't want to go that route. Or import a CSV library. Java does not have a built-in CSV parser like Python does, so it would be an external library. We'd have to import it into the project using the pom.xml. Import a library, and then teach you how to use that library and use that library to parse. Again, that would be a distraction from what we're trying to do. I wish it were as simple as Python, import CSV, and then CSV.parse, I think is the syntax for that. So we went with let's curate the data and just split on commas and move on with what we actually want to talk about, which mainly this week is testing with files, which we'll start that conversation Wednesday. So we're just going to do line.split. Syntax is the same as in Python. Just whatever string you have, .split on some delimiter, and it's going to split the values on that delimiter. So if I have the string ABC and I split it on commas, I'm going to get an array list with the value A, B, and C. Line.split, this is another one where we're just going to use array lists. Line.split returns a plain old array, a Java array, which if you want to just work with the array, fine. I'm not going to stop you. It's perfectly fine. But if you want just an easier way, if it's something you don't want to think about, if you don't want one more thing in your head while you're working on the homework assignments, this arrays.asList, we've seen this quite a bit as well. Arrays.asList will convert this array into a list like we had in the previous example of reading all lines. And that list we can jam in the constructor of an array list to get our values in an array list, which we're comfortable with. We're used to working with array lists. And we also want to parse numbers. We have, I guess, only one number in the homework, the rating for a song that you have to parse. If we want to parse numbers, if it's an integer, integer.parseInt. If it's a double, double.parseDouble. When we read a file, we're going to read it as a string, so all of the numeric values will be strings, and then we can use these parse methods to get those strings into the data types that they represent in double. This will only work if the values are well-formed, if we have well-formed numbers, meaning that if the value doesn't clearly indicate a number like this, if we say parseInt of 4, which we know as humans that's the number 4, the method isn't going to know that. It's just looking for numeric values. And for the case of parseInt, just numeric values with no decimal places. So this will crash, and it will throw, I forget the name of the exception, but some malformed number exception, I think. Something like that. and the program's going to crash unless you catch that. That's one exception we don't expect you to catch. The only exception we expect you to catch is the I/O exception. This error would be, I don't know. It could be something we could have you catch, but I don't know. We decided not to. We're not going to bother. If this exception is thrown with the data that we're working with in class, it's going to be because it's a bug, and that's something you got to fix, not an error with the data. We could have you sanitize data, and sometimes, occasionally, if somebody could, it's happened in the past a little bit, if somebody gets data into the ratings.csv in the song ratings app that is corrupted, that will break your code, if that happens, then that's the only time you would see this error. Other than that, it's going to be a bug that you have to fix. Okay, any questions on all that? Okay. Now let's write some code. So the rest of the week is going to be live coding. That's the only slides I'm going to do all week. Add commas to your passwords. Yeah. Hopefully nobody out there is just parsing. Out in production, you shouldn't be parsing CSV, just splitting on commas. Hopefully they're not doing that. So let's write some code. I want to write a method named load countries, which is going to take a string that we're going to interpret as a file name to a file with data in this format. A country, city, region, all as strings, population as an int, Latin long as doubles. And we want to get this information into a hash map of strings, which will be the countries, to array list of cities, which will be all the cities in that country. We didn't get through this whole example in the previous lecture. I don't expect to get through the whole thing in this lecture, so we'll get us hopefully to the same spot-ish, and then we'll pick it up next time. So here's the cities file. Oh, spoilers. IntelliJ does not like, this isn't that big of a file, but IntelliJ doesn't like opening files of any moderate size at all. So here's the file. The countries are going to be their 2-digit country code, the name of the city, a 2-digit region as a string. When I had this as a homework assignment before, and that really tripped students up. Most of the region codes are indicated as numbers in the data, but they are actually strings. Most notably, when you get to the United States, the region is the 2-digit state. It's going to be a string, and if somebody's parsing Texas as an int, would cause some issue. The population, and then lat long, the location of that city. And this file has quite a few cities, nearly 48,000 cities in this file. So this is one of the big advantages of using files is we can work with a lot of data. We can process a lot of data without too much code. There's no way I'm going to manually do anything with all these cities. I'm not going to do anything 47,000 times, but I'll write a loop in a few lines of code to process this data and get all of the data in a way that I can work with it in my code. So let's do exactly that. So the first thing I'm going to do is stub out this method and then write a main method to call the thing. We'll do testing on Wednesday. So for now, I'm just going to write a main method. So public, this will be a static method. Task 7 will have you writing static methods again. At one point I said we'll never write a static method again, but it just made sense for these ones to be static when we're reading these files. And we're going to return a hash map of string to array list of city. I'll take a quick timeout here because we don't have a city class. So let's create our city class. And this code is in the repo, but I'm live coding it. I'll do a few things different, just whatever I'm feeling at the moment. So this will be a little bit different. But private, go string name. Come on. Name, region, country, population, which is an int, latitude as a double, and longitude as a double. Whenever you're having IntelliJ generate anything for you, I kind of regret showing this in class, but not much because I'm going to do it today too. But always be careful when you're having IntelliJ generate code for you to make sure it's generating what you expect and that it's doing the right thing. So I have name of the city, region, country, population, latitude, longitude. Looks good to me. I'm going to create some getters. We don't need setters because the city's not going to change. We're not going to update the population as children are born or anything. And a toString method, because why not? I'll just use the default toString. And that's my city class. So the getters are just the auto-generated, what you would expect. We call this, I don't think I've ever said this in class, but we call this a POGO, or a POJO. Yeah, POJO, which I hate that acronym, but plain old Java object. It's just an object that has private variables, a constructor which sets them all, some getters. I guess I don't have the setters, so it's not strictly speaking. And then a toString, just the standard stuff. Plain old Java object. Load countries, I'm going to cut and paste to make sure I don't have typos, as though I were submitting this to Autolab. String file name, and stub it out. Then I'm going to write a main method. String file name equals. So when we open the file, well, let me get the rest of the code out here. Hash map of string to array list of city actual equals load countries of file name. And then for now, we'll just print actual. The file name, when you're working with data, at least in 1.16, we're going to always put it in a folder named data, which is in the root of your project. This is where Autolab is going to look for your data files. So make sure you have these in the right spot. This is where your data files are going to be. This is where my cities.csv is. And when I open the file, when your code always runs from the root directory when you run in IntelliJ. And that's the same place where I'm going to run your code from in Autolab. Autolab will run from the root directory. So make sure everything is where it's supposed to be and you're reading the files as expected. You should have data/file name. So in your tests, when you're generating your test files for task 7, make sure every file name that you read in your test is data/file name. Don't hard code, and I'm sure this will be some office hours and Piazza questions anyway. Don't hard code data anywhere into your code. Some people in like their read songs method will say data plus file name and wonder why it doesn't work in Autolab. Make sure in your test your file name is data.cities.csv, and that's the argument that you're giving your method. So this is our usage that's set up. We're just going to print whatever we return to the screen. Now we're ready to open a file and read the contents. So files.read all lines, paths.get, file name, and so I don't have to work with lists. I would just work with lists, but to make it not as, just to make this consistent with the slides, I'll use array list. Array list of string lines. My goodness, I can't type. And I want to initialize my hash map. countries equals new hash map. And I'm going to eventually return countries. And right here, I'm going to get an error. IO exception is an exception that Java won't let you not catch. And this is where you really need to be careful with IntelliJ generating code for you. The tool can always help, but if you don't know what you're doing, it can definitely hurt you. The very first thing it'll suggest for this error, and I swear when I see this in office hours, I'm not going to, I don't know what I'll do yet. Depends what mood I am that day. But if you do the autocorrect, it's going to add this throws IO exception, which means I know this code throws an exception. I'm not going to catch that exception. I'm just going to throw it to the stack frame that called this method. And then the program's going to crash because that stack frame isn't going to catch the exception either. Don't do that. Do not just say throws in your code. For what it's worth, that's what read all lines does. It throws an IO exception, and that's why Java knows that you expect this exception to be thrown. Instead, we're going to write our try catch. I'm going to try. I can wrap this whole thing in my try catch. I'm going to try to run this code. And if it throws that IO exception, why did it? And E is just a variable name. Just to prove that point, I'll call this exception. And if you use the auto-generated code in IntelliJ to generate your try-catch block, you'll get this print stack trace. What this will do is print the stack trace that you see when an exception is thrown that you don't catch. So you can print that out if you want to see the stack trace. For our purposes, let's just return a new hash map. So if the file doesn't exist, we're just going to return an empty hash map, which is consistent with the homework. You'll return empty array lists, empty data structures if the file is not found. And we're just going to have to leave it at that today, and we'll parse the rest of this next time. The music's about to cut me off.